Okay, so here's your quiz, guys. Okay, we got watch for units. Okay, units are kind of crucial here. Okay, it's a 200 Newton box sliding down a 20-degree incline. Acceleration is 1.5 meters per second squared. You're looking for the force of friction. Okay, and for the second one, the curler is throwing an 18-kilogram curling rock, applying a force of 86 newtons forward. The acceleration of the rock is 3.5 meters per second squared. What's the force of friction between the rock and the ice? This one is during the pushing phase. Okay, the one on your practice test was actually after it was released. Okay, so this question works a little differently than the one you had on your practice quiz. Okay, this one is while the curler is actively pushing it forward, not after they've released it, and that changes things considerably. Okay? All right. Mrs. Sikora, if you can pause it here, please, and let the students finish their quiz, and then you can mark it after. Okay, a name on it, pass it on to somebody else, guys.
So last call for any grade 11.
Okay, watch and listen carefully up here, guys. So for question number 1, right, on question number 1, we have a 200 Newton box sliding down the 20-degree incline. So here's our incline. And when they tell me the box is 200 newtons, which force did they tell me? They told me the force of gravity, right? Okay, so I'm going to have force of gravity here, and I know that it's 200 newtons. All right, normal force is going to go right here, even though we're not going to need it for anything. And then this side, the important side, it's F parallel. We know this angle is 20 degrees, so that means we know this angle is 20 degrees. All right, and then it also tells us that we are looking for the frictional force even though it's sliding down. So force of friction should go up. 1 mark. That's their givens. There's their free body diagram, etc. Okay, one of the things I need to do right now is calculate the mass of the box. They told me the weight of the box, but if I'm going to do this question, I need the mass of the box. So I need to do this calculation here, where I use the force of gravity, which they told me, divided by the acceleration due to gravity in order to get the mass. So that's 200 newtons divided by 9.81. Okay, so they're going to get a mark for this step. Okay, so we'll have our 200 newtons, well, not 20, 200 divided by 9.81. Okay, so 20.39 kilograms, okay, which I can also put inside the box. All right, 20.39 kilograms, and the next thing, sorry, they're going to get a mark, sorry for that. Okay, the next thing I got to calculate is F parallel, which is the opposite side of the triangle inside here, right? So I'm going to go that F parallel will equal the force, or sorry, the sine of 20 times the force of gravity, 200. I'll get a mark for that as well. All right, so our F parallel is 68.4 newtons, which then can go here. Okay, so I'm trying to find the force of friction, and they told me the acceleration. What can I find with the mass I calculated and the acceleration? F net. All right, that's my next step. F net is going to be m times a, which is going to be our 20.39 with all the decimals, okay, times 1.5. So that would be their 4th mark. Okay, so 20.39 times 1.5. Okay, so my net force is 30.58 newtons down the ramp. Okay. So I've got my net force. What's the other way to calculate net force?
The sum of all forces.
Right, the vector sum of all forces. Okay, so on this one here, that's going to mean, okay, that F net equals F parallel plus the force of friction. Okay, and I'm trying to find the force of friction. Okay, so force of friction will be F net minus F parallel. So that will be 30.58 newtons minus 68.4 newtons. They're both the same direction down the ramp. Okay, and that will give me my force of friction, which will be my fifth and final mark. Okay, so I'll have my 30.58 minus my 68.4. All right, so I get a negative number here because I made down the ramp positive, so friction is acting up the ramp. I have two significant digits, so I will have 38 newtons up the ramp. They must have both, okay? The right number of significant digits and up the ramp in order to get the marks for the answer. Okay, 5 marks there. Questions on number 1? Okay, for question number 2. Okay, so in question number 2, our free body diagram, which is our first mark, is going to look like this. We have an 18-kilogram curling rock. It is being pushed by the curler using an applied force, okay, of 86 newtons. Okay, the acceleration of the rock is 3.5 meters per second squared, right? And we are looking for the force of friction acting backwards. 1 mark for Gibbons. What's the next thing I should calculate? Net force using F equals m times a. That's what I have right now. Okay, F net equals m times a, 18 times 3.5. Give him a mark there. All right, so my net force is 63 newtons forwards. Okay, what should I do next?
Should it be your force of friction?
Yeah, now I calculate force of friction using
F net and your acceleration. When you order, should it be your
okay, I already did m times a. What's the other way?
all sum
Sum of all forces. Okay. So F net equals the applied force plus the force of friction. Okay, I'm trying to find the force of friction. Okay, so force of friction equals F net minus the applied force. Give them a mark for their sum of all forces work. So that's going to be 63 newtons minus 86 newtons, okay, because they're both forwards. Okay, and so 63 minus 86, I can't believe I just put that in there. Okay, 23 newtons backwards, or I even accept negative because it didn't ever say forwards on here. Oh, it did say forward, so it has to be backwards. Okay, so 23 newtons backward.
Good job.
4th and final mark there. Okay, give a mark out of 9 at the top. Let them see it, and then either bring it to me or to Mrs. Sikora. Okay? Mrs. Sikora, you're going to want to pause it here. Okay, so I want to keep throwing more examples at you, okay, today, right? Looking at different ways that I could ask an inclined plane problem, or a vector problem, or a static condition example, okay, those kind of things, because there's all kinds of ways, permutations, combinations of ways I can give you things and make you calculate things in these types of problems. So today is a gain experience kind of day, all right? So I am going to have up here to start with another example. And it is this one right here. So very much like the quiz question, the first quiz question, I have a 340 Newton box being pushed up a 30-degree incline at a constant velocity
Could we have
of 1.5 meters per second. The applied force up the ramp, so the force being used to push it up the ramp is 200 newtons. What is the force of friction? Okay, this is an example where people forget something important involved with all inclined planes. Okay, so it's an inclined plane question. Okay, get it set up. I'll give you 5, 8 minutes, something like that, to work on it, and then we'll go through it together. All right, so Mrs. Gore, I'm going to pause it here now. Okay, so for this one, we want to draw our inclined plane, okay, as our kind of first step here. All right, we know it's a 30-degree angle. We know the weight of the box is 340 newtons. Okay, so we know the hypotenuse of that triangle, because the hypotenuse of the triangle is always the force of gravity, and it's 340 newtons. All right, everybody okay with that so far?
Yes.
Okay, we also know then that the triangle that's internal, okay, has another side that's normal force, which we still haven't used yet. We won't use it until after I teach you how the force of friction works and how it's related to normal force, so basically that's just going to be there for nothing for a while. Okay, and then we've got this side here that ends up being parallel to the plane, okay, that is F parallel, and that angle's 30 degrees. All right, so the other things we know, or actually the thing we should calculate first is the mass, just like we did on the quiz question. Okay, we were told the weight, we need the mass. Okay, so we're going to go 340, our force of gravity, divided by 9.81 to get our mass. Okay, so it's 34.66 kilograms. Okay, so now I can put that inside the box. Now I can put the other forces on my free body diagram. The applied force is 200 newtons, and it's up the ramp. So I know that force is 200 newtons. What are the other two forces? Not the numbers, but what are the forces?
The force of friction and F parallel are going down.
Right, force of friction, which we know always opposes our motion downwards, and they tell us we're looking for the force of friction. Okay, and this is the one that people forget, F parallel. Okay, sometimes people read this question and they just go, oh sweet, 200 newtons up the ramp, ooh, done. Okay, and they forget that there's always F parallel. Anytime you put something on an incline, F parallel is there because gravity is there, and the normal force are there. Okay, and they always combine to produce this force. So, if I want to get the force of friction, I need to calculate F parallel and the net force, okay, which I haven't done yet either. So I'm going to calculate F parallel. F parallel is always calculated the same way. Okay, F parallel is always the opposite side of that triangle, so some combination of this. Okay, sine of 30 times 340, right? Yeah. All right, sine of 30 is 0.5, so we're looking at 170 newtons, I believe. Probably shouldn't do math in my head, but I did. Was I right? All right, so 170 newtons is our F parallel. All right, so I've got F parallel there. Now I got to calculate what? Before I can calculate force of friction, I got to get one more thing. Net force. Okay, I don't have the sum of all the forces yet. Okay, and I need that because right now I have two unknowns, F net and FF. I can't calculate them both using sum of all forces. So I've got to calculate F net. I know the mass because I calculated it. I know the acceleration because the question told me what it was. All right, so I'm going to take my 34.66 with all the decimals in my calculator, okay, times the acceleration, 1.5, because obviously we want to keep all of our decimals all the way through. So times 1.5. So my net force is 51.99 newtons up the ramp. Okay, that's going to be important.
How come that net isn't zero if it's a constant?
Oh, sorry, it said constant velocity of, see?
Yeah.
That trick that I played on you, I played on myself. That's embarrassing. And it's recorded. And Mrs. Sikora is going to see it. That's so embarrassing. Okay. That's awful. Pretend you never saw that. Thanks, John. I would have really liked that. Would have been even worse afterwards. Okay. So, F net is 0 because, as I should have pointed out and been more aware of, it's moving at a constant velocity. Shame on me. Okay, so it was moving at a constant velocity. If it's at a constant velocity, the acceleration is 0. And thus, when we do the operation I was just about to do incorrectly, it's still valid to do this, but with the right number, 0. Okay, 34.66 times 0 is 0. So my net force is 0 newtons, and now I can calculate the force of friction because I know all of the other forces. F net is F parallel plus the force of friction plus the applied force. Those are the three forces that are contributing to my net force. All right? Since my net force is 0, I know that these two forces have the same magnitude as FA. The force up the ramp and the force down the ramp have to be equal if our net force is going to be 0. So really what I'm looking at here is that F parallel, okay, well actually 0 minus F parallel.
So friction would be 30 newtons.
We'll get there. Not there yet. Okay? Minus the applied force, okay, equals the force of friction. Now I can put in all my numbers, so 0 minus 170 minus 200. That one has to be negative. Why does the 170 have to be negative?
Because 0 subtract anything just means.
No, I went 0 minus negative 170. Why did I make the 170 negative? I have to make it opposite up the ramp, right? And I made this 200 positive, right? So I have to recognize those vectors. Yeah? Okay, so I'm going to have 0 minus negative 170, so it's positive 170, minus 200, well, that's going to be negative 30 newtons, but I can't leave it as negative. I have to say it's down the ramp. Okay, so the force of friction is 30 newtons. Down the ramp. Okay? All right. So, is it easy to mess this up? It is. Okay? Like, you got to read the question carefully. I wasn't being very mindful when I read that question. All right. One more incline plane. Child is sliding down a 25-degree hill on a sled. It's not snowing yet, but it's in the forecast. Okay, not till tomorrow. Probably won't stick, but okay, it's a winter-themed question. So a kid is sliding down a hill, 25-degree hill, on a sled. Friction is resisting with 150 newtons. The child's mass is 50 kilograms. What is their acceleration? Okay, this one's actually easier than the last one. Okay, less calculated. Mrs. Sikora, you're going to want to pause it here, please. Okay, let's have a look at this one. So we want to set it up like we set up any inclined plane. Okay, first we draw it. All right, we know that the angle is 25 degrees. Right? This is the child. They're very square. Okay, and they have a mass of 50 kilograms.
Could we have grade?
All right, so we got our 50 kilogram mass. Then we draw our internal triangle that is always there because it is the vector sum of the two forces that act on anything on an inclined plane. Normal force and the force of gravity. This time, we're not given the force of gravity. Every other one we've done today, they told us the thing in newtons. This time we actually have to calculate the force of gravity, so we have to go 50 times 9.81, and that'll give us 490.5 newtons. right? So now I've got the force of gravity, 490.5, right? And I know the angle, 25, so I can get F parallel. Okay, so I'm going to calculate F parallel, same way as always, sine of 25 times the force of gravity, 490.5. $207.29 newtons down the ramp. Okay, so now I can put that on here, 207 newtons. All right, friction is resisting with 150 newtons, so that must be up the ramp then, and I'm going to put that on there. What's my next step? F net, using sum of all forces, right? Okay, so F net's going to be 207.29 newtons down the ramp, okay, minus 150 newtons, okay, because it's up the ramp. So take that number there and we'll subtract our 150. Okay, we're actually adding a negative here, but right. So our net force is 57.29 newtons down the ramp. Okay, now that I've got that, can I calculate the acceleration?
Yeah.
Using?
F net divided by mass.
Right, F net divided by mass, or F net equals m times a. Okay, the two methods we use in every single Newton question. Right, so 57.29 divided by 50 kilograms. Okay, is going to give us like 1 point something.
Just 1.1.
1.1. Okay, we have two significant digits only here, so 1.1 meters per second squared down the ramp. Okay, everybody good with that one? All right. So, I want you to try a few now off of the digital workbook here. We did a couple of inclined plane ones yesterday. So I want you to try some of the vector ones today. I would like you guys to do number 6. Sorry guys, I can't write on this part here. Okay, so I want you to do number 6. Number 10. Okay, so 6 and 10 from the forces of vector quantity worksheet. That's the bottom of page 4. Right, so 6 and 10, and 11. 6, 10, and 11 for right now. Okay, because those are vector ones. We've done 3 inclined planes, so let's do 3 vector ones. 6, 10, and 11. About that. All right, so 6, 10, and 11. I'll try and make that a little bigger and see if it'll fit on there. Just so it doesn't fit. Now it'll fit. Okay, there you go. 6, 10, and 11, guys. Okay, let's have a look at number 6 here. So we got the 2 children making a snowman. Okay, and they're just pushing a big ball of snow to do that. The big ball of snow is 50 kilograms. And one of them is pushing it due west. with 110, oh, that's awful. 110 newtons, okay, worth of force, and the other one is pushing it with 130 newtons worth of force, 15 degrees west of north. Okay, so there's north, this would be 15 degrees, okay, and this will be 130 newtons. So, I mean, probably not the most productive way to push a snowball with two people, but it's what's going on in this question. So if I look at this and think kind of logically about it, which way is this ball going to go?
Northwest.
Northwest, yeah, okay, and probably a little more west, or maybe a little more west than north, but not much. Okay, this is gonna end up being like pretty much northwest. Oh, yeah, the answer says pretty much straight northwest. Okay, so what do I have to draw next? This is my free body diagram. It just tells me my givens, basically. What do I have to draw next?
Vector diagram.
Yeah, I gotta draw a vector diagram. These are vector quantities. If I'm gonna find my net force, I've gotta find the vector sum of all forces. It's just a little more work than it is on an inclined plane or, you know, a curling rock or something easy like we've been doing. So I'm gonna have my 110 newtons due west, and then so this will be y, this will be x, this is 15 degrees, and this is 130 newtons, which means my net force goes like this. And holy smoke, is my scale ever good. Okay? This is like really close to what it should be. All right, so I've got to calculate now my F net, which means I got to do vector additions. So I've got to find the x and y components of all my vectors. All right, the x component of this one is 110 newtons. The y component of the black one is 0. Okay, the x component of the purple triangle is the opposite side, so I'll go sine of 15 times 130. So that side is 33.64 newtons west. Okay, and the y component is the adjacent side, so cos of 15 times 130 is 125.57 newtons north. All right, now that I've got those things, now I can find red x and red y. Right, so I've got to add the two x components together to get red x. They both go west, so that's easy. Okay, I take the 110 newtons west and I add it to the 33.64 newtons west, and I get 143.64 newtons west. Okay, and then my y component, well, there's only one. Okay, the first vector didn't have a northerly component, so red y is equal to purple y and is 125.57 newtons north. Okay, now that I've got those two, what do I do? Got the two sides of that triangle. Yeah, do Pythagorean theorem to get F net, right? I said the hypotenuse of that triangle is my net force, so that'll be 143 with all the decimals squared, plus 125 with all the decimals squared. All right, so square root of our 125 squared plus 143.6464 7586 squared. All right, so my net force is 190.79 newtons. Okay, and I need its vector, so I've got to find theta. Okay, so I can use tan for that because I know the opposite and adjacent sides. So tan to the minus 1 of the way I drew this, x over y. So that'll be the 143.64 divided by the 125. So second 10, 143.6464, 7586 divided by that number. Okay, gives me 48.8 degrees, and that will be west of north, the way I drew it. 48.8 degrees west of north. Now, that's not what the question asked for. The question wanted the acceleration. So I've got to take that 190.79, which is my net force, and divide it by the mass, which was 50 kilograms, to get my acceleration. So 190 divided by 50. Of course, we're keeping all the decimals, obviously. Divided by 50. And it is 3.8 meters per second squared. At 48.8 degrees west. Oh, sorry, I have 3 significant digits, don't I? So 3.82 meters per second squared at 48.8 degrees west of north, or if you had the complementary angle of 41, 42 point, no, 41.2 degrees north of west, you'd also be fine. Okay, is that one making sense? Spoiler alert, a question very much like that one has appeared on virtually every unit exam I have ever given in this course for this unit. Yes, you can. All right, so let's keep going on those other ones here, guys. I don't know how far along everybody is, but let's keep going on. We said, right, 6, 10, and 11, right? Yeah, so keep going on 10 and 11. All right, want to have a quick look at question 11 here, okay? Just because this is one that has kind of it's a simple trick, but it's there, and we need to kind of recognize what's going on. So in this situation, we've got, that we know the acceleration, okay? We know the acceleration of the system is 2.15 meters per second squared, okay? We know there's no friction, and we know that this mass here is 2 kilograms. That's the mass that's going to drive the system because of what force? Gravity. All right, so I can quickly calculate what the driving force in this system is by simply calculating the force of gravity here, okay? And that will be 19.62 newtons, 2 times 9.81. Everyone all right with that? Okay, since there's no friction, that is also my what? Net force. That's my net force. It's the only force. So what I just did there was the vector sum of all forces, that one. Okay, it's the only one. So now that I know my F net, I should be able to use m times a to get the mass. But when I do this, what am I calculating the mass of? The system, and that's what people forget. If I put this question on a test, I get 9.13 kilograms all the time. Okay, because people forget that when they do this, they are calculating things about the whole system, not one part of it. Okay, so if I'm calculating mass here, that's going to be my 19.62 newtons divided by 2.15, which gives me 9.13 kilograms, and then I have to subtract the 2 kilograms worth of mass that were here, okay, to get 7.13 kilograms. That's a pretty heavy cart, given that our carts were only 700 grams with all the crap put on them. okay, the other day in the lab. So this is obviously a much bigger scale, okay? All right, for number 10, okay, we've done lots of pulley questions. Again, it's just a system. It's like question 11, okay? You know the masses, so you should be able to calculate the acceleration of the system and then extrapolate that to mass A. This should say 2.8 meters per second squared up, and I think it does on yours, okay, but it doesn't here. Okay, up. All right, listening here, guys. Reminder of your lab reports, okay, that they are due next week. So make sure you're working on those, okay, getting them done, so that you can hand them in on time. We're going to be kind of moving out of Newton's second law and into Newton's third law here by next week. Okay, we'll have an assignment on Newton's second law that you'll hand in for marks, like your vector assignment in the last unit. So that'll be coming up as well. Okay, and then we'll be moving into conservation of energy and work energy theory. Okay, so things are kind of moving along here, and we'll probably be looking at a unit exam 2.5 weeks or so. Okay, so we're going to get through this pretty quickly. We've got another lab and stuff like that yet too, but okay, just to give you a bit of a timeline, that's what we're looking at. Okay, all right. Okay. And you can keep working on those, guys. If there's still time, you can keep working on the other ones. Okay, you can do 12. You can go back to the incline planes. Okay, whatever else.